these properties is what we would like to have in our distributed representation that we usually call word embeddings. So word embeddings are basically distributed representation that are trained in a way that expose these properties that we saw before. And there are many, many algorithms to create word embeddings. And in this presentation, I will focus just on two of them, word-to-vec and fast text. In particular, word-to-vec is not the first approach trying to generate word embeddings, but it's definitely a very important one because it generates word embeddings with a very efficient algorithm. And because of that, and it was the one that really spread this idea of word embeddings in the NLP area. So that's why we start with that. So word-to-vec is, yes, a way to compute word embeddings. As I said, is based on a very simple linear model. So that's why it's very, very efficient. And it is strongly inspired by the distributional hypothesis. So if you remember the distributional hypothesis, we kind of summarize that by saying a word that was able to create a link between a word, the context of the word, and the semantics. And word-to-vec is really building on top of that to create this useful distributed representation. There are actually two versions of word-to-vec, continuous bag of words and continuous skipgram. We will mostly focus on the first one, but I will also give the intuition about the second one. So the idea with word-to-vec is we have a very simple task. Given a sequence of text, let's say 5 words, a sentence, we will mask the word in the middle, and we will ask the model to predict that word back. So it's a very simple task, and this is, you can see the example here. So you see that we have this Alan Turing lived in England, so that's the sentence. Now I will mask the word lived, so I end up that the input for my model is Alan Turing in England, and the output for the model is to came back with the word that I just masked, which is lived. So here, just to make it again clear, the input is the part on the left, these 4 words, and the output is the word on the right, which is this lived. And the model actually is very simple. It's all here. So we really have just 2 matrix multiplication, one here and one here, and one average in the middle. So it's an extremely simple model. And going more in details, so here the first thing we do is actually we came up with the one hot representation for the word, which we said that we don't need and we don't like this representation, but here is just to start the model. What we really care is what happens after the first multiplication. So these red vectors here, this is the embedded or let's say the distributed representation, so the word embedding that we are trying to compute. And you see that the model is coming up with this one word embedding per word. It's summing all of them together, so we have one vector at the end. And then we use what we called before a projection to come up with the score for every possible word in output. Softmax as usual, and then we extract the highest score, which in this case hopefully is lived. So the interesting thing about this model is that actually we don't care too much about the task and we don't care too much about the model. We only care about this part here. So hopefully, in order to solve this task that is not so interesting for us, but in order to solve this task, the word-to-vec algorithm is forced to somehow create this interesting representation for every word that is capturing this semantic information associated to that word. And in fact, this is exactly what happens. And in fact, the plot that you saw before, the country capital relationship is taken from this paper. So you see that by training in this way, we are really creating some link between the word and the semantics. And I mentioned that there is another way to run this. And in fact, we can do the opposite. So before we went from the context to the masked word, but here in the continuous skipgram version, they do the opposite. So they go from the word to the context around the word. I will not go into details, but I will just say that this approach seems to work better if you have a small amount of data. That was word-to-vec. There is another word embedding algorithm that I want to talk about, which is fastText. And actually is from the same author, and is strongly based on word-to-vec. So the algorithm is pretty much the same. What it changes here is that instead of considering just a mapping from the word to an embedding, we also decompose the words. You see it here, like I have the word where. I decompose the words into various n-gram. So here I'm just plotting the 3 grams because it's easier. But so you see that I have all these components, and I will create one embedding for every one of these components, and then sum all of them together. And the intuition is that by doing that, I can probably get more interesting morphological information, because I can look at the various components of the word, and for example, in English, I can see that if one of these components is ly, I'm probably talking about an adverb. So I can now incorporate this information in my final embeddings, which is the one here on the right. And another very interesting advantage is that it helps with out-of-word tokens. So if you remember, out-of-word tokens are these tokens where that have not been seen in training. So like in this example here, maybe you have this case where, and this has not been seen in training. So here we don't know what to put. But most probably, we have seen some of these pieces about where, and maybe somehow the model is able to come up with an approximate semantics for the words. So this is definitely giving more information than just having zero information about that word. So it can help with morphology, and it can help with out-of-vocabulary words. And there is one interesting aspect here. If we use word-to-vec, fastText, on all these algorithms, what we are basically doing is some sort of transfer knowledge that you have also seen yesterday. Because basically what we do is we use the task that we saw before, so word-to-vec, to train these embeddings. So we call this part pre-training, because it happens before we start the train on the task that we're really interested in. Then we take these embeddings, and we will use these embeddings in the model that we are really training. And the advantage of doing that is that in this pre-training phase, the task was unsupervised. So I can run that on a lot of data. And because of that, I can extract, hopefully, a lot of syntactical and semantic information. And then I can move on my supervised task, the one that I'm really interested in, and as it usually happens, here I will not have too much data, but I can somehow exploit the information that I extracted from the first phase. And we will see that this idea of pre-training, we will exploit this a lot in the following 2 systems that I will present.